Chapter 1: The Information Revolution in Physics. It began not with a bang, but with a whisper. A soft realization that something was missing from our understanding of the universe. For centuries, physics had been concerned with the tangible. The energy of motion, the force of gravity, the speed of light. Newton gave us apples and falling bodies. Einstein gave us time that bends and stretches. And then, quantum mechanics startled us with its mysterious probabilities. And, spooky, connections. We learned to live with the uncertainty. But beneath all of this, behind the spinning electrons and the dancing fields, lay something subtler, almost invisible information. Information isn't just a concept for computers or phone lines. In physics, it means something deeper. It describes what we can know about a system, how its internal pieces are related, and what we lose when things change. The realization that information might be just as fundamental as energy was for many scientists. Like waking up to discover that a silent language had been speaking beneath every experiment all along. Entropy was the first hint. In the 19th century, entropy was born as a measure of disorder, of heat dispersing and things falling apart. But over time, we came to understand it as something else. A way to count the missing information about the microscopic state of a system. When your cup of coffee cools, it's not just energy spreading out. It's also the universe losing track of the precise motion of trillions of molecules. That loss of detail is entropy. Then came quantum entanglement, a pair of particles separated by light years, but still mysteriously linked. If you observe one, you instantly know something about the other, even if they've never talked. Einstein called it spooky action at a distance. Others saw it as an unavoidable side effect of quantum rules. But a few began to ask a bolder question. What if this flow of information, the way one particle seems to know about another, is not a bug, but a feature? What if it's as real and as physical as gravity? And so, a new idea began to form quietly, like mist, collecting in the hollows of our best theories. What if information is not just a bookkeeper that tracks the universe's transactions, but a player on the field? What if it has its own momentum, its own current, its own force? What if the flow of information, the rise and fall of entropy, is something we can describe with equations, measure with detectors, and understand with the same clarity that we apply to mass or motion? This is the world that gave rise to RUEQFT, the Renormalizable Unified Entanglement Entropy Quantum Field Theory. It is a mouthful, yes, but the idea it represents is breathtakingly simple. Treat information specifically, the entropy and entanglement between parts of the universe, as a real, physical thing that moves, evolves, and interacts. But here's the catch. If you try to just plug entropy into the standard equations of physics, things break. You get infinities. Nonsense. You try to add a drop of wine to water, and the glass overflows. Mathematics resists you. Early attempts to add entropy directly into the Lagrangian, the function that encodes all physical interactions, failed. The couplings weren't renormalizable, meaning the theory spiraled out of control. When you zoomed in too closely, then, something changed. A researcher named Lee proposed a way to make entropy not just an extra term, but a first-class citizen in the equations, by redefining it as a gauge invariant operator. In simpler terms, he found a way to make entropy compatible with the symmetries of nature. The result was a theory where the information flow, the current of entropy, could be treated just like electric charge or energy. This breakthrough allowed physicists to begin building a new kind of field theory, one where entropy and energy are woven together, one where the very flow of information can create resistance, mass, even time itself. In this video, we will explore that theory not through the lens of raw equations, but through the ideas that give them meaning. We'll travel from the quantum world of entangled particles to the searing heart of a nuclear collision. We'll see how information might bend the laws of time near a critical point, and how the damping of waves in matter might be a symptom of entanglement, flowing like a hidden current. We'll even step back and ask the big questions. What does this theory tell us about the nature of reality? Can information be more fundamental than space and time? Welcome to a new kind of physics, one where the silence between things might be more important than the things themselves, one where the universe whispers not in particles but in bits. And it's time we start listening. Chapter 2: When information flows like a river. Imagine a field of golden wheat swaying in the breeze. The wind moves invisibly, yet you know it's there because the wheat responds. It bends. It dances. Now, imagine a similar kind of wind, but not one of air or heat. Imagine a wind made of information. In the classical view of physics, the only currents that mattered were those of matter and energy. Rivers of electrons powering your phone. Waves of electromagnetic radiation traveling from the sun to the earth. But if we accept that information, that mysterious property, which tells us something about the state of a system, is also a physical quantity, then we must ask, can it flow? Can it ripple, collide, or get tangled up, just like other physical things? The Renormalizable Unified Entanglement Entropy Quantum Field Theory, RUEQFT, says yes. It proposes that there is such a thing as an information current. Like wind through wheat, this flow affects the systems it passes through. And in the quantum world, where particles and waves blur together, the consequences can be profound. Let's make this concrete. In the RUEQFT model, every quantum field, whether it describes a particle like a pion or a field like the Higgs, has a hidden partner, its entanglement entropy. This is not just an abstract number, like how hot something is or how fast it's moving. This entropy evolves, it pulses with the field, and it can be written down mathematically as a kind of density, like the mass of fog per cubic meter. From this, we define a four-dimensional entropy current, a quantity that flows in both time and space. Think of it like a weather forecast at every point in space. And every moment in time, this current tells you how information is moving, just as a wind map tells you where the gusts are blowing. But here's the twist. Just as wind can push a tree, the flow of entropy can change the behavior of physical systems. It's not just a passive background, it interacts. The theory introduces two key quantities, lambda t and lambda x, which describe how strongly entropy flows in time and space. If these two numbers are different, if entropy prefers to move more easily through space than through time, or vice versa, something remarkable happens. The equations of motion for the field begin to shift. The damping of oscillations changes. The waves decay faster or slower, depending on the direction the entropy flows. This leads us to one of RUEQFT's most fascinating insights, a new quantity called d delta eta, which captures the difference in how entropy influences time versus space. When d delta eta is 0, you're in familiar territory, classical hydrodynamics. But when d delta eta is positive even slightly, you enter a new regime where information reshapes reality. Let's say you have a pseudo-Goldstone boson, a kind of gentle excitation in a broken symmetry field, like a ripple in a bowl of jelly. In standard physics, its damping rate, how fast it fades out, is proportional to the square of its mass. But in RUEQFT, the entropy current tilts this relationship. The damping rate becomes proportional to the mass raised to a new power 2 plus d delta eta. Just a small change in the exponent 2.018 instead of 2 can mean a 10 to 15% shift in measurable quantities. In the razor-sharp world of particle physics, that's a thunderclap. And it doesn't stop there. This new exponent d delta eta introduces something wild, a thermodynamic analog of Einstein's special relativity. You may remember that in special relativity, time stretches and distances contract depending on how fast you're moving. Now imagine a similar stretching not of time or space, but of the very rate at which a system comes to rest. When information flows faster in time than space, the system's internal clock ticks differently. It relaxes more slowly, as if time were stretching out not because of motion, but because of information flow. To describe this, the theory borrows a term from relativity, gamma th, an information Lorentz factor. It depends on the system's correlation length, how far one part of the system talks to another, and d delta eta. When the universe becomes more entangled, gamma increases. The system becomes heavier in information terms. It slows down. It resists change. All of this may sound abstract, but it's not just math on a chalkboard. Experiments in high-energy physics, ultra-cold atoms, and condensed matter are now beginning to measure the subtle fingerprints of d delta eta. And if they confirm its existence, we will have caught our first glimpse of information as a fundamental force. So here, in this chapter, we've met the rivers of entropy that flow unseen through the fabric of fields. We've learned how they introduce new behaviors, new exponents, and new kinds of relativity. And most importantly, we've begun to understand that the world is not just built from particles or fields. It's also sculpted by the quiet but powerful flow of information. In the next chapter, we'll see how these entropy currents don't just affect the decay of things, but also how they might be responsible for their very mass. If you like the content of this video book today, please subscribe and like it. I look forward to seeing you again next time. From Thothsam Science Catch.